Okay, section 10.2, electromagnetism, where electricity and magnetism come together. And if you're watching this on YouTube, you're missing these wonderful lectures. One of my favorites, you take some total cereal, which is iron fortified, and you crush it up, and then you put a cow magnet in there, which is a very, very strong magnet, and you get little iron bits attached to the cow magnet to show that, yes, indeed, there is actually iron in your total cereal. Other ones you're just going to miss out, so it's all right. So, okay, let's talk about electricity and magnetism. April 21st, 1820, incredible discovery. Hans Christian Ørsted, who was a scientist, was lecturing, and he recognized that when he flipped on a battery, it caused a compass needle that was nearby to suddenly deflect. And he thought that was strange and interesting. So it was an accidental discovery, but then he took it and didn't just say, oh, that was weird, and ignored it. He actually studied it and tried to figure out, okay, what's going on here? Why does turning on this battery cause this compass to deflect? And so he found that, in fact, if you have a current traveling through a wire, it will generate a magnetic field. So in the example on the left, where you have no current, and this is a series of a whole bunch of compasses, and right now all of the compasses are just all pointing north to geographic north. Then you add a current to go into your current carrying a wire. So maybe you attach a battery to it, and you're going to get, that was supposed to be the other way around, but let's make that one a large one. No, actually better that way. Okay, so then you got the current carrying wire coming through. Here's the plus side. Goes through your wire. When you get a current traveling, then you set up a magnetic field. And you know you have magnetic field because these compasses are now pointing in the direction of the magnetic field. That's what compasses do. They point in the direction of a magnetic field. So it appears that there is some sort of magnetic field that's going around the current carrying wire. That's what this compasses would indicate. Well, it turns out that in fact you do. If you have a current, we talk about the magnetic fields, and we call them B field lines. I don't know why we call them B field lines instead of M field lines, but we do. We call them B field lines, as opposed to E field lines, which are electric field lines. So the B field lines go in a circle, in concentric circles, around a current carrying wire. So in this case, the current is going in the down direction. Then you're going to get the magnetic field is going to be going around this side in front and then around and back. So it becomes important to understand, given which direction a current is going, what direction does the magnetic field go. And so we have a handy-dandy rule to help us remember, which is the right-hand rule. We actually have several right-hand rules that we're going to be using with electricity and magnetism. So we call this one the curly hand rule, because you curl your fingers, or the golf club rule, because it's like gripping a golf club, where you wrap your fingers around and then you point your thumb down the shaft of your club. So the idea is you wrap your fingers around the golf club, or the current carrying wire in this case, and you point your thumb. Your thumb is pointed in the direction of the current. So your thumb goes in the direction of the current, and the direction of your fingers and the way they wrap, this is with your right hand, will indicate the direction of the magnetic field. So in this case, it's going to go around this way. So you get a better view of it over here. You have current going up. You wrap your finger around, you put your thumb in the direction of the current, you wrap your fingers around, and you can see that there are these circular way magnetic field lines, concentric circles that travel around the current carrying wire. So that's the curly hand rule, or the golf club rule. We can set up or create our own little magnets by having currents traveling through wires. So a magnetic field line can encircle a current carrying wire, we know that. So if you take that wire and you bend it into a loop, then what you get is this bunching up of magnetic field lines in the center. So they're all going in the center, and they're all going in the same direction. So if you add another loop, you're going to get twice as much bunching up inside that circle, and all of the circles are going to be pointing the same direction. I guess I'll back up. I thought it was going to be more on that one. So what you can do by having several loops of coil that wrap around, you can generate a magnetic field that tends to go, let's say that the current's going in this direction, then I'm going to put my thumb in that direction, and I'm going to put my thumb in that direction, wrap my fingers around, and what I'm going to find is that I've got a magnetic field that tends to be coming out through the center of the coil, and it's going to be wrapping around. So it's going to come through the center, and then it's going to wrap around the back side. But each of those is going to come around. They might go around this way, they might go around the other way. But there's going to be a whole bunch of lines coming right through the center of the coil, and that becomes really useful if you want to set up a magnetic field somewhere. You just have to wrap a bunch of wires around, and making sure that the current's always traveling in the same direction. If you want to calculate the magnitude of a magnetic field near a current-carrying wire, then you use this little formula. B, that is the magnitude of the magnetic field, and the formula is the mu sub 0, which is one of those really cool universal constants. It is on your formula sheet, called the permeability of free space, times I. I is the current that is traveling through the wire, and then 2 pi r, r being the distance from the wire. So if you have a wire like this, okay, then you would have current traveling up it like so. Well, you might say, well, what's the magnitude of the magnetic field over here, okay, at this point right here? Well, your magnetic field is going to be traveling kind of in a circle like this, right? You're going to go with your right hand rule and wrap around, so it's going to kind of go this way, all right? And so, but the question is, how strong is it out here at this little blue spot? Well, the strength of the magnetic field is B equals mu sub 0 times the magnitude of this current, whatever that current is, times this radius, 2 pi, times the radius right there. So that whatever that radius is from the wire, that's going to tell you the magnitude of the magnetic field at that point. The SI unit for magnetism, or magnetic field, is the Tesla, with a capital T. That's the unit. Okay, electromagnetism. If you put many loops together, this is kind of what I showed you before, except now it's sort of nicely aligned. If you have a series of loops together, and around every little part of the wire, you're going to have these circular loops of magnetic field wrapping around, well, what you get is this really high density of magnetic field lines all through the center of your coil. So what it ends up doing is those magnetic field lines, they go through the center in this direction, they come out the end, and then they kind of loop back and come through again. So this starts to look a little bit like a bar magnet. And the bar magnet, remember that would be the right side, the red side, right? So that would be the north side of your compass, where the magnetic field lines kind of come out and then go back in. So they come out of the north side and they go into the south side. Oops, that went the wrong way. There we go. And that's going to go that way. So when you have this loop of coils, you can generate a magnet much like a bar magnet. We actually call this kind of coil loop a solenoid, and we'll be using those and playing around with them in our labs. If you put a coil of wire and you insert a ferromagnetic core, like a nail or a paper clip, anything ferromagnetic, inside a coil, then it's going to strengthen the intensity of magnetic field. So you can make actually a stronger magnetic field by putting some ferromagnetic material inside, and that you have just built what's called an electromagnet. In other words, it's a magnet that works as long as there's an electric current flowing through it, and then when you disconnect the battery or whatever is giving you the current, then the magnetism stops and the electric field desists, and the magnetic field desists, and therefore it stops being magnetized. So an example of an electromagnet is the little magnet that we used in the Monkey and the Hunter demo. When we were holding that little monkey up, we attached the monkey with a magnet to an electromagnet that was connected to a battery. When we shot the little ball at the monkey, it broke the circuit, which caused the electromagnetic to disconnect and drop the little monkey. So yeah, electromagnets is actually super useful devices. In order to use, in order to build an electromagnet, you have to have what's called a soft magnet. In other words, a magnet that will become quickly magnetized, but then will also become quickly demagnetized. You don't want to have a hard magnet, first of all, because you can't magnetize it, and then if it did get magnetized, it wouldn't demagnetize. So a soft one that will have its domain shift really quickly and then shift back. That's what you want when you're building an electromagnet. Okay, so a couple questions to close out the discussion. Which of the following has just one magnetic pole? The pieces of a bar magnet cut in two, a small piece cut from the end of a bar magnet, a proton, an electron. The answer is none of these. Even an electron that's spinning would have two poles. There is no such thing as a magnetic monopole, at least that we know of so far. The north magnetic pole of a compass points toward, okay, think about that one. What direction does the north magnetic pole of a compass point? Does it go to north geographic pole, the south geographic pole, the Earth center, or none of these? Well, the answer is the Earth. If we call this geographic north and geographic south, when you put a compass in the magnetic field, it's always going to point to geographic north. And that is counterintuitive, because if you had a north bar magnet, then the compass lines are going to go like this, coming out this way. And in this case, when you put a magnet, it's going to be pointing towards, here's your magnet, it's going to be aligning the magnetic field, so it's going to point towards the south pole. So the answer is that a compass in a magnetic field, so let's get the magnetic fields here. Magnetic field, this is the Earth. The compass in a magnetic field is always going to point towards, in the Earth, it's going to point towards geographic north. Or it will point in the direction of the magnetic field lines. So in the case of the Earth, magnetic field lines are going towards the pole at the north geographic pole. But because all the lines are going in, and that's the direction that your compass is going to point, this up here would be, this up here, where all those lines are going in, is going to be the south magnetic pole. So while it is geographic north, it is magnetic south. That concludes our lecture.